Hi, and welcome back to what will be the last of our videos on the periodic table. This time we're going to talk about trends in chemical properties. Again, these will be relating back to the ideas of core charge, distance from the nucleus, electron configuration, and how our valence electrons are arranged. First of these is defining our elements as either metallic or non-metallic. This is something that you should be very used to in terms of the structure of the periodic table. So the elements on the right-hand side of the periodic table are non-metals. These are the ones that tend to form covalent bonds, include our halogens, noble gases, elements such as carbon, nitrogen, and sulfur, to name a few. All the other elements, except our metalloids, are metals. Okay, so as we progress from left to right across the periodic table, the elements become less metallic. They are less likely to lose electrons to form positive ions as they react and are more likely to gain them. This idea of something being metallic or non-metallic is defined as metallic character, and the metallic character varies as we move from left to right across the periodic table, from metals to non-metals, and can vary down a group. Okay, for metallic character in group 1 and 2, it increases as we move down the group. However, by the time we get to group 13 and particularly group 14, this can differ greatly as we start with non-metals at the top of group 14, move through some metalloids and into metals. So it's not consistent down a group. But as we move left to right across a period, we do see a distinct decrease in metallic character. The other thing that we can talk about as being a trend is melting point variation. So the melting points are dependent on the structure or bonding present in a substance. So for period 3, from left to right, sodium, magnesium, aluminium, and silicon, it will increase, but then it decreases sharply. Okay, so as we move from left to right across the period, the melting points of the metals tend to increase, but when we hit non-metals, because of the nature of their bonding, we see a sharp decrease in the melting point. This is because of the different types of bonding, from metallic through to covalent, that we observe. Of course, silicon and carbon can form giant covalent molecular lattices that we'll learn more about in term 1. So this is going back to our physical trends. So our atomic radius, ionization energy, electronegativity, cation and anion radius, and melting point are summarized in this table. So looking at our chemical properties, the similarities between group members arise because of their similar electron configurations. Because they all have the same number of valence electrons, and valence electrons determine chemical reactivity, it's our electron configurations that are critical when talking about these properties. So if it has one valence electron, like those in group 1, okay, these are going to be very reactive. They have low ionization energy, so will readily form compounds. The metallic character itself is defined as its ability to form, to react with water. And we see that with sodium. When sodium reacts, it reacts quite violently with water, producing sodium ions, hydroxide, and hydrogen gas. That hydrogen gas is flammable. If the reaction gets hot enough, the gas will ignite. These elements also produce distinctly colored flames due to the absorption or emission of light. And this is that light, the color is dependent on the energy of transition of the electrons. They have low melting points and boiling points compared to other metals, and they react easily with other elements such as halogens to form ionic bonds, such as what we see when we react sodium with chlorine to form sodium chloride or salt. So when we look at the chemical reactivity of metals, the metal reacts with water is an indication of its overall reactivity. The reactivity of group 1 metals is higher than group 2 because of their lower core charge, so they have lower ionization energies, and so the reactivity increases as we move down a group. We can see this with sodium having a vigorous reaction, right down to potassium and rubidium having violent explosions because of the exothermic nature and the rate of production of hydrogen gas. When we move to group 2, magnesium won't actually react at room temperature, but if we react it with steam, it will start to react, and calcium will have a slow reaction at room temperature. Remember, calcium is lower in the periodic table than magnesium, so it should have a greater reactivity. So when we look at the differences between group members, remembering that these are all in the same column as the periodic table, we can see that they have different densities and different reactivities. The more reactive you move down the group, the first ionization energy decreases. So we also see a lower melting point and boiling point moving down because of the larger size of the atoms. The density, and remembering that density is given as a mass divided by volume, okay, also increases as we move down. Sodium and potassium will float on water, whereas rubidium, cesium, and francium sink. So the density increases as we move down the group as well. When we come to the halogens, so moving all the way over to the other side of the periodic table now, we're in non-metals, their reactivity is opposite. So for metal reactivity, as we move down a group, metal reactivity increases. Okay, for the halogens, as we go up a group, then the reactivity increases. If you think about it, this makes sense because halogens want to gain electrons, so the more electronegative the atom is, the more likely it is to gain an electron, and that is how halogens will react to complete their octet, whereas metals want to lose electrons, so low ionization energy, those that are lower in the group, will be more reactive. So with this, they will react with each other, displacing in similar ways to metal displacement reactions, but reactivity increases down the group because we are going to be having the same core charge, and that will be reducing the attraction of the electrons to the nucleus as we get further away, and we also decrease our electronegativity. So remembering that in order for nonmetals to react, they need to attract electrons, so lower electronegativities will result in lower reactivities. So this diagram here summarizes that information for you. Because the reactivity of nonmetals is determined by the electronegativity and atomic size, it is dependent on the element's ability to form negative ions or to draw electrons to itself to form covalent bonds. So this decreases down a group and increases across a period. So again, fluorine, which has our highest electronegativity, is also our most reactive nonmetal, whereas cesium, which has our greatest electropositive character, or our smallest electronegativity, and is largest atom, so is most easily able to lose its electrons, is our most reactive metal. These are the displacement reactions that halogens will undergo. It's not necessary at this stage for you to memorize these. You should just remember that fluorine is more reactive, and just as we see with metals, a more reactive nonmetal can displace a less reactive ion from solution. And these will also undergo precipitation reactions, which we will look at again later in the year. So the other thing to make note of is as we go across a period, particularly period 3 in the periodic table, there is a change from metallic to non-metallic character, and this changes the way in which atoms will react with water. So metallic elements, the oxides or oxides of metallic elements, will react with water to form sodium hydroxide, a strong base, which is where they get their name alkali metals and alkali earth metals from, because they will form alkali solutions or solutions that contain hydroxide ions on reaction with water. On the other hand, our non-metal oxides, such as sulfur trioxide, carbon dioxide, nitrogen dioxide, when they react with water, they form acids, and these are critical in our environmental chemistry because it's these gases which are produced from the burning of fossil fuels, such as sulfur dioxide, sulfur trioxide, and nitrogen dioxide. These are burnt and given off when we burn oil and coal and things like that. These then move into our atmosphere and cause acid rain because the gases react with water in the atmosphere, forming sulfuric acid and nitric acid, which then is rained down on the environment as acid rain. So this is a summary again of period 3 elements, and this looks at the element type. Of course, these are metals, metalloid, non-metals, and this starts to lead into what we will look at again later in term 1 when we come back from our summer break, in terms of the type of bonding that these elements will undergo. Of course, metals will exhibit metallic bonding, non-metals exhibit covalent bonding, carbon and silicon form giant covalent networks that we will learn more about, and then when a metal reacts with a non-metal, we get an ionic bond. So this picture here gives a summary of the trends. You should annotate your periodic table with these trends. They are the ones that you are expected to know in terms of metallic character, atomic radius, electron affinity or electronegativity, and ionization energy. And I will see you in class for us to have some practice on writing these explanations in terms to questions, as well as discussing the different trends. Just a note on noble gases. These were thought to be completely inert, and they used to be called inert gases. However, we know now that they are just highly unreactive. There are a couple, xenon in particular, that can react under very special circumstances. These highly unreactive compounds arise from their very stable electron configuration, having complete octets in their valence shell. So therefore they're very stable. They are unlikely to gain or lose electrons. So don't forget those when it comes to chemical properties. Sometimes they can be overlooked. That's it from me, and I'll see you in class.